Dear students, I welcome you for the today's lecture related to the shell and tube heat exchanger general design considerations. We have already discussed the design procedure, 11 step design procedure. However, on which side the fluid will be allocated, what should be the fluid velocities, what should be the pressure drop, what should be the stream temperatures, and based on the physical fluid properties what are the mean and average temperatures, that these are considered to be the general design considerations. So generally this is the basis for consideration or allocation of the fluid, or either on the shell side or on the tube side, on which side I have to allocate a certain specific fluid, either on the tube side or on the shell side. So fluid allocation, then fluid velocities, then stream temperatures, pressure drop, and fluid physical properties. So one by one we will study the fluids which are corrosive in nature. They should be kept on the tube side. Why? Because when the fluid which is corrosive in nature, that will be only corroding the inner surface of the tubes, and as a result I can select a material with a proper material of construction for the tubes. You can say also we can do that for a shell also, but the cost involvement for the shell is more in comparison with the cost involved for that of the tubes, and that is why the manipulating with the tubes is more cheaper as manipulating with the shell. So the corrosive fluid, or you can say the fluid which are harmful, which are corrosive, they are to be allocated on the tube side. Even if the fluid is fouling, that is going to affect the surface area of the tubes, that is to be selected for the tube side only. So if they are producing the fouling, that we will be providing it on the tube side, inside of the tubes, so that my outside tubes as well as the outside of the shell, that will be clean. So two surfaces are affected if the fouling fluid is kept on the outside of the tubes. That means the shell side. So shell is affected as well as the tube outside, that is affected. And cleaning the tube outside of the tubes is more difficult than cleaning the inside tubes. Inner surface of the tubes, that can be easily cleaned. Outer surface of the tubes, which is accommodated inside the shell with a certain pitch, it is more difficult to clean. For cleaning purpose, it can be a chemical cleaning, or you can have the high pressure nozzles for cleaning the outer surface or the inner surfaces of the tube. The next is the fluid temperature. So fluid temperatures are there. So high and moderate temperatures of the fluids are on the tube side. It is general consideration. It is not necessary, it can vary, but generally the higher and moderate temperatures, they are on the tube side, because when even unnecessarily if we have touched the outer surface of a shell, that will not damage the human beings, that will not burn the human beings, and that is why the hot fluids, they are preferred inside the tubes. Then next is the operating pressure. Higher pressures on the tube side. Why higher pressure on the tube side? Because we can use the sufficient thickness for the tubes only. And if the high pressure fluid which is on the outside of the tubes, you will require both a heavy shell as well as the heavy tubes. Both will be of a higher thickness if operating pressure is on the tube shell side. So it is better to have the higher operating pressure on the tube sides, so that we can only increase the thickness of the tubes, because we are calculating the thickness of the tube, which is equal to the PD upon 2FJ upon 2FJ, which we have discussed in the subject of process equipment. So this is the thickness, calculation of the thickness. So calculation of the thickness of the tubes as well as the calculation of the thicknesses for the shell, that is of concern. Then pressure drop, lowest allowable pressure drop on the tube side. Pressure drop allowed, lowest is on the tube side. Now if the flow is turbulent, then come to the viscosity. If the more viscous material, then the flow is turbulent, then we can use it on the shell side. And if the flow is laminar, we are going to use it for the tube side because of the velocity considerations. Turbulent velocity है, turbulent flow conditions है, that means you are having the higher velocities. If the velocities are high, that means the heat transfer rates and heat transfer coefficients are good. Heat transfer coefficient values will be more if the velocities are more. H is your heat transfer coefficient, and this H is depending on the Reynolds number and Prandtl number. And Prandtl Reynolds number incorporates the calculation of the fluid velocity. And that is why the turbulent and the laminar flow conditions, for turbulent flow condition we will prefer the shell side, and for low fluid velocities, that means the flow is laminar, then we are going to use it for the tube side. The next is the stream flow rates. Stream, hot stream as well as cold stream. So lowest flow rates on the shell side. Lowest flow rate on the shell side, so that we will be able to manage the pressure drop. Out of the above points, which factors are dominant are to be given on the priority, and accordingly the selection has to be done. So it is not always that for the corrosive fluids you are using the tube side, fouling fluids you are using the tube side. If the fluid temperatures are high, again on the fluid side, operating pressure is high, again on the tube side. If the pressure drop is there, that is lowest allowable pressure drop on the tube side. So maximum is related to the tube side. Then the viscosity, if it is more, then the flow is turbulent, then it is shell side, and if the flow is laminar, then it is tube side we can use. So one has to remember the general design consideration for the fluid allocation, which will be depending on the corrosion, fouling, fluid temperature, operating pressure, pressure drop, viscosity, and the stream flow rates. The next is the fluid velocities. What should be the proper fluid velocities which will give the good heat transfer coefficient? There are so many researchers, they have worked till now in the world. based on the heat transfer coefficients. And they have concluded that the fluids which are on the tube side, they should be having the velocities around 1 to 2 meters per second if it is a tube side fluid, and if it is a shell side fluid, then 0.3 to 1 meters per second should be the fluid velocities. This is general design consideration, considering the pressure drop, energy losses, the maintenance and operating cost. So this tube site I can manipulate with the 1 to 2 meters per second, and for the fluid side it becomes 0.3 to 1 meters per second. The high velocities, if the fluid is with a high velocity, they will provide the higher heat transfer coefficient. But for the higher velocities, your pressure drop that will be also high. Velocity flow conditions, that is the turbulent flow conditions for higher velocities. But on the contrary, you will be having the higher pressure drops. Whenever the higher pressure drop, that means my operating cost is more. So while selecting this operating cost, one has to look into the matter related with the velocities. So then velocity must be the high enough to prevent any suspended solids which can settle. That means the fouling should not take place. Fouling that can be reduced or minimized with the proper selection of the velocity, and then to reduce the fouling ultimately. That means it is prevented by suspended solid settlings, but not so high as to cause the erosion. Erosion is, that is basically the metal is getting consumed because of the high velocities. So liquid velocities, fluid velocity should not be such a high so that the metal is getting eroded, but they should be sufficient to prevent the suspension of the to maintain the suspended particles into the fluid like motion, as a result to reduce the fouling process. For that purpose, this experience of 1 to 2 meters per second on the tube side and 0.3 to 1 meters per second on the shell side, that is there, but not so high as to cause the erosion inside the vessel. Then vapor velocities will depend on the operating pressure and the fluid density. Vapor velocities that will depend on operating pressure and the fluid density. So if the vessel is operated under the vacuum, then the velocities of vapor that will be around 50 to 70 meters per second. These are the velocities of the vapor, and these are the velocities of the liquid phase. This is for the vapor phase. Vapor velocities will depend on the operating pressure and the fluid density, out of which the 50 to 70 meters per second is the operating velocity for the vapors. Then the atmospheric pressure, if it is there, then it is 10 to 30 meters per second pressure velocity, they are sufficient. And for higher pressure, it is 5 to 10 meters per second of required for the high pressure vessels. The next is the stream temperatures. The closer the temperature approach used, the difference between the outlet temperature of one stream and the inlet temperature of the other stream, the larger will be the heat transfer area required. Now, this figure, that is your temperature profile diagram, as the temperature difference TH in minus TC in. This is, say for example, in a co-current fluid, and THO minus TCO on the another side. Now, in case of a counter current, you will be having the opposite of that, that is THI minus TCO, so that THI minus TCO and THO minus TCI. So this side temperature difference and this side temperature difference, they are of more concern. The greater temperature difference should be at least of 20 degrees Celsius, and the least temperature difference, that is of 5 to 7 degrees Celsius, for the earlier using cooling tower, that is 5 degrees Celsius for the refrigerated brine. That should be the stream temperature difference. The next is the pressure drop. That is, the designer is free to select the pressure drop, but by considering this pressure drop, my operating cost increases, and as a result there is a need to study the economic analysis. So based on the economic analysis, one has to optimize the operating pressure drop. What should be the operating pressure drop? Theoretically you can have any pressure drop, but practically and economic aspects, it becomes the general range again given by the scientists which have performed the pressure drop calculations in case of our shell and tube heat exchangers. Then the liquid velocities, if it is a liquid velocity less than 1 millinewton second per meter square, we are having the 35 kilonewton per meter square is the pressure drop. And if the liquid viscosity is in between 1 to 10 millinewton second per meter square, then the accepted pressure drop is between 50 to 70 kilonewton per meter square. Now if it's a gas and vapor, it was the liquid viscosity. Gas and vapor, if it is a vacuum, then the 0.4 to 0.8 kilonewton per meter square pressure drop is accepted. If it is a high vacuum, then we can accept the 0.1 into absolute pressure. If it is in between 1 to 2 bar, that is 0.5 into system pressure, that will be there. Then above 10 bar pressure, that is the 0.1 into the system pressure. So these are the different pressure considerations. If the pressure are more than this, then I have to manage or manipulate the exchanger layout. Whatever the designing procedure we have studied, there we have to manage the exchanger layout. Exchanger layout, that is to be managed if the pressure drops are above these limits of, for liquid, 35 kilonewton per meter square. That again, that depends on the viscosity. The next is the physical properties of the fluid, that is your density, viscosity, lambda latent heat of vaporization, thermal conductivity, and the Cp values. All these values are evaluated at a mean stream temperature, that is the average temperature of the each stream. This is the THI plus THO upon 2 or TCI minus TCO upon 2. These are the mean stream temperatures for the hot fluid and the mean stream temperature for the cold fluid. Now if the temperature differences are significant, then the heat transfer coefficients are calculated at the stream inlet temperature and the outlet temperature. So we are going to calculate the heat transfer coefficient based on the inlet temperature or outlet temperature, and whatever the lowest value of the heat transfer coefficient that is used for calculations. Now if you will see the temperature difference, that is a very high at this end and very low at this second end. So as a result, my heat transfer coefficient that is going to vary. So if the temperature differences are significant, then the heat transfer coefficients are calculated at the stream inlet and the outlet temperature. The lowest value of the heat transfer coefficient is used for calculation purpose.